We all know the atomic bomb is very dangerous. Since it may be used against us, we must get ready for it, just as we are ready for many other dangers that are around us all the time.
All right, so what are some of the things that we can use nuclear chemistry for? And again, this is Coach Miller and Mr. Bunting. And we're jumping right into one of the common uses for nuclear chemistry. There's a phenomenon that actually goes on called carbon-14 decay. And what exactly is that all about?
Well, carbon-14 has a very specific half-life that we can measure. So we can take the isotope carbon-14 that comes off of normal carbon and find out how long this organism has been on the Earth and how long it has been decaying for. So it tells us the history of an object.
Okay, so once the carbon-14 stops decaying, I guess we know that substance is dead or something, right?
Right.
Yep. Okay. So we could, I guess, go back and figure out its lifespan, and that's kind of how paleontologists do their work, right?
Mm-hmm.
Awesome. And you just be familiar with this chart. Just understand, basically, a living organism is absorbing carbon-14 as it's living, and when it dies, it obviously is in the ground and will become a fossil after a certain period of time, and then we can go back and figure out, okay, when did this substance stop absorbing carbon-14? That's how we figure out its dating.
Is this going to be 100% effective at all times? There's a lot of controversy in the news about it.
It's, it's pretty close, but it's kind of a hit or miss thing, I think.
Okay.
So, why is nuclear chemistry even important?
Well, because nuclear chemistry is a completely different type of chemistry than what we've been talking about these past 13 units. For chemical reactions, you can see that's all basic stuff that you know. We form new substances based on the elements. We take the positive charge from one element and put it with a negative charge of another element and do those double displacement reactions. With nuclear reactions, we're focusing just on the nucleus. So we're going to form a different element from one element, and we're going to produce those particles or different forms of radiation from there. So there's a big difference between the two that you're going to need to be able to classify a reaction as nuclear or chemical based on these definitions.
Cool. So, what I'm taking from these is that a nuclear reaction deals with, obviously, the nucleus. So we're dealing with protons and neutrons, right?
Yep.
And what we've done up until this point just deals with electrons.
We talked about that in the first video.
So, outside of the nucleus.
We're talking about it twice. Do you think this is important to know?
Probably important.
All right.
So the amount of energy, obviously, in an electron is substantial, but it's nowhere near the amount of energy that we find in the nucleus. All right, so now we need to get into actually writing a nuclear reaction. So we've talked about the different types of decay. Now we need to see what that actual reaction is going to look like.
All right.
So here's the basic steps. We want to set up two equations, one using the mass and the other using the atomic number. Calculate the missing mass number, calculate the missing atomic number, and then use the atomic and mass numbers to determine the identity of our missing particle.
So it's basically two math problems, the top numbers, and then do another one with the bottom numbers, and then you figure out what element based on the bottom number, right?
Right, because the bottom number is that atomic number.
All right.
Okay, so here's our first example. So here's what we're talking about. Draw a line there, and draw a line here. 29 and 0. So think of this as your equal sign. And on this side of the equation, over here, what plus 0 is going to give me that 29?
29. Easiest question you'll ever be asked.
Awesome. So anything plus 0 is that number. And what plus a negative 1 is going to give me a 12?
Well, 12 minus 1 would be 11. So 11 plus negative 1, is that right? 13.
I'm gonna
13 minus
I'm going
1
to go with
is
your second
12.
answer. So 13 plus a negative 1, or 13 minus 1, essentially is that 12. Hey, it's early. We're not even through our first cup of coffee yet.
How did
So,
it start?
we take that 29, we're going to put it up here. Take that 13, and that's going to go down here and be my new atomic number. So then I can go on my periodic table and find element 13, and I see that element 13 is no longer magnesium, it is
Aluminum.
aluminum.
So we can see how we started with one element, went to another element without reacting anything. So this is clearly a nuclear reaction.
A nuclear reaction. So something happened in the nucleus as far as decay would be concerned. All right. So let's go over some specifics here, because you're going to need to know these and be able to identify them on a test or on a quiz. So the first one is alpha emission. We talked about alpha emission is simply a helium nucleus.
Easy enough.
And I know that a helium nucleus has a mass of 4 and an atomic number of 2. So that tells me right here, I've got 2 protons and 2 neutrons. And if I emit 2 protons and 2 neutrons from a nucleus, that's going to obviously have a huge effect on my nucleus. And you can see here americium or americium, however you want to call it, and neptunium is my resulting element. So obviously my alpha particle, or I can know that this is alpha decay because 241 and 237, there's a difference of 4. So I know that 4 is my mass number, because remember, this is hyphen notation. This right there is hyphen notation. So 4 is my mass number. I know that I would have emitted a helium nucleus. So those are my 2
There, easy
products.
enough. Alpha emission emits an alpha particle.
Okay.
Wonderful.
Beta emission simply emits a beta particle. So the decay of carbon-14, you can see we lose an electron, and it's really a negatively charged particle from the nucleus. We'll get into the actual details of that in class and kind of talk about how that is even possible. Beta decay actually causes that element to change from carbon to nitrogen, but my mass stays the same. Positron emission, similar to beta emission, but now we're emitting a positive particle, and we can see the resulting element in that case.
If this is confusing you guys, go back and look at your symbols for beta negative and beta positive, which is positron emission. You'll see what's actually changing there. That'll make this a lot clearer.
Okay. And the last one is electron capture. So the word capture obviously means that that nucleus is catching something. So we're adding something to the nucleus, and it would have an effect. And you can see the change here. We go from beryllium to lithium. We go from element number 4 to element number 3, and obviously we see a change in the number of protons there. And the last one is gamma emission. Notice that gamma rays are emitted either alone or with other types of radiation. They do not change the mass number or atomic number because they're simply energy.
So this is the only type of nuclear reaction to know that does not actually change the identity of the original element.
Right.
There might not be any grown-ups around when the bomb explodes. Then, you're on your own.